Okay, everyone, let's get started. Sorry, I'm running a little late. So last lecture we covered the branch and jump instructions. I think I got through it all, but I'll just quickly go over this just to make sure everyone's clear on this. So we have branch and jump instructions. Branches are conditional, jumps are not. With branch instructions, they use the B-type format, which is pretty similar to the I-type. Pretty similar to I-type, but it's not. It's B-type. And the main challenge here is figuring out how to calculate the offset for the branch. And so in order to simplify that, I gave you the code, which I believe is correct. If anyone finds an issue, let me know. So the branch offset is instruction bit 31 concatenated with instruction bit 7 concatenated with instruction bits 30 down to 25 concatenated with instruction bit 11 down to 8. And then that would give you an address that is a 16-bit address. So then I add a 0 to make it an 8-bit address, a byte address. And then we later strip 2 bits back off, which, you know, is kind of redundant. But this branch offset is 12 down to 2, which converts it to a word address. Now you might say, why are these bits all scrambled? Why is it 31 and 7 and then 30 down to 25? I don't know. I wish one day I'll figure it out why they just did it like that. Don't know. Is it because they want to keep the other stuff in the same place? Maybe. I don't know. I know they're trying to make the hardware as simple in terms of the implementation and the way the wires are routed. But anyway, so there's the code for you. Then we have jump instruction, which is a J-type, which looks kind of like a U-type, but it has some additional immediate bits, but they're scrambled. So the J-type offset, the J-type offset, which is used for JAL instructions. I believe this is the only instruction that uses J-type, is JAL. Is instruction bit 31, then 19 down to 12, and then 20, and then 30 down to 21. So again, if you just use this code, you should be okay. If you find any errors with that, let me know. So the question is, what do you do with this code? I mean, after you put it in, you're generating a signal here called JAL offset. In the previous slide, I called it branch offset. What do you do with that? Where's it go? Those values are going to go into a mux, which is going to allow you to select a next value for the program counter. So this is a new mux. Sometimes I just call it the program counter mux or the PC mux. And hopefully you remember from 2.12 this was covered for the MIPS architecture, and they had a signal in there that controlled it called PC source. So I've adopted the same name, PC source. So it's the source for the next program counter, what the program counter will get in the next cycle. So the control unit will then set that. So PC source is going to end up being, it's selecting between PC plus 1, which is what you guys used before, just go to the next instruction, or the branch target, sorry, not target, but address. The branch address, the JAL address, or the, what's the third one? Jump register address, right? JALR address, right? So there's 3 potential target addresses in the instruction, depending on if that instruction were a branch or a jump register. You guys with me? So there's 3, like every instruction that comes in, you'll be setting these 3 signals. For most instructions, the signals are garbage because it's not a jump and it's not a branch. But if it is a jump or a branch, then you'll have a valid offset calculated in the execute stage. So as soon as the instruction comes into the CPU, into the execute stage, you'll have 3 potential targets that you may want to go to in the PC in the next cycle if you're dealing with a branch or a jump, if it's a branch or jump. So what happens is the control unit will resolve, if it's a branch, the control unit will resolve the branch, meaning that it'll determine whether the branch should be taken, and the way that it's going to signal that is by setting PC source to 1, assuming 1 is your branch offset address. And then if it's a jump or a jump register, there's no resolution. It will just automatically, blindly just set the program counter to the address that's targeted by the jump or the jump register. You guys with me? Does it make sense? So all you have to do is make a mux and use it to modify your fetch stage. So your fetch stage, I think originally I gave you code for the fetch stage, but it was limited because the program counter would all it could do is count up by 1. Whereas now we have this option where we can pick count up by 1 or branch address, JAL address, or JALer address, right? Okay. And then the program counter source is, where is that? Right here. Program counter source, PC source EX. This is generated from the instruction in the EX stage. Okay? So this is really just a trinary, like an assign or an assign statement or an if statement, depending on whether you're doing it in an always or not. Okay? Actually, I think that'll be in an always, right? Because your PC isn't an always because it's clocked. Okay, then I mentioned stall EX, which is just a bit that comes out of the control unit that's set to 1 if you want to stall. Stalling means that whatever instruction is being fetched, it's going to just get ignored, but it's too late to not fetch it. It's too late, because the idea is that by the time the control unit figures out what the stall signal is going to be, the next instruction is already fetched. It's basically, it's too late to do anything about it. You're going to get it, right? And this is true for every modern processor, that whenever you have a control instruction, branch or a jump, you're going to pay for it in terms of stalls. You're going to have, like no-ops dynamically shoved in the CPU, right? Which is why code that's got a lot of branches and jumps in it is slower than code so if you have a modern CPU and you compare a matrix multiply, which is basically, aside from the loop structure, it's all always does the same thing, versus like finding out how many Facebook friends separate me from him, the matrix multiply is going to have a higher throughput because it's going to have less of these stalls, right? So okay. So that's the only additions to the fetch stage. And then in the rest of the CPU, and I think this might be it, actually. We've got the mux. There's a mux here that had a third port that we weren't using, the reg select. And this just gives us a pathway to take the program counter and shove it in the register file. And we have to do that whenever we have a jump and link instruction, because jump and links will save the return address, which is the address of the instruction that appears in the code after the jump and link. So it gives you a way to return to where you were before you jumped, right? It's a return, right? It's a subroutine return. And so there's a little nuance here, though, because the program counter that you want to feed in there is the program counter associated with the instruction that's in the execute stage, because the jump and link will be writing the register in the write back stage, which means the program counter that you want to put in there is the one from the execute stage, right? In other words, right, because the instruction in the execute stage is the stall. It's the one that they call it the fall through instruction. It's whatever comes immediately after the jump, right? So whatever instruction is in the execute while you're writing back is the previous instruction. Sorry, not the previous. Sorry. It's the next instruction, right? Because the way the pipeline works is the instruction that's later in the pipeline, right, comes before the instructions that are earlier in the pipeline, right? So the instruction that's being executed is got an address PCEX associated with it, and so that's what we want to write back when the jump and link is in the write back stage, right? So we can sequence things correctly. Okay, so that's basically just the delayed form of PC fetch. I mean, it's not hard to implement that. You just have, you just clock PC fetch and make it PCEX, and you got it. Okay. All right, so I think that's all of the structural changes. The last thing you have to take care of is branch resolution. So in the program, in control unit, you guys are currently not having any feedback. You guys have a control unit right now where instruction comes in and you translate each instruction into a set of control signals. So it's an open loop style, right? You just say, you know, I'll take an input and I'll spit out an output, right? The problem with branch resolution is you have to now have a closed loop thing where you're going to set up the CPU and then you're going to base for other outputs on what comes back from the CPU, right? Now this gets this is risky. This is a really easy way to end up in a combinatorial loop. So the easiest way to do this is to use a nested if statement, where you say if the instruction is a branch, then set up the ALU, and then inside there you say if the ALU reports that the inputs are equal, then take the branch or not take the branch. If you set it up as a nested statement in the control unit, then you don't risk changing the inputs to the ALU based on the output of the ALU, right? You don't want to do that. You don't want to change the inputs based on what it's outputting, because that'll end up that'll blow up, right? You got to make sure that regardless of what the ALU does after you set up the branch, that you don't change the inputs. You have to stabilize the input. So again, the way to do that is just an if statement, a nested if statement. And you guys are already using nested ifs in your control unit anyway, right? Because you got to say I think most of you do anyway, right? Because you look at the opcode, and then inside there you look at the funct and things like that, right? You guys with me? Okay, so use a nested if statement, and then this table shows how to interpret the output of the ALU, and also what to do with the ALU. So if it's a branch if not equal instruction, then you tell the ALU to subtract, and then you use the 0 flag from the ALU to determine whether you take the branch, because branch if equal and branch if not equal are resolved by subtracting the two values and checking to see if the result is 0 or not, right? However, if you're doing a branch if less than, you have to tell the ALU to perform a set less than operation, and then you look at the R output of the ALU, right? Now you might say, wait a minute, why don't we just take that table and stick it outside the control unit and just make a separate branch controller? Well, yeah, you could do that too. Yeah, if you want to. Right, I'm assuming that you guys are going to want to make a monolithic control unit. Just stick all the control inside one big glob. But other people may say, that's why not just have a separate control unit for the branch resolution? That's up to you. You can do that. I try to, you know, I'm just giving you a hint to try to make it as easy as possible to try to minimize the complexity of the design. But that doesn't mean that's the best way to do it. I don't, you know. Okay, any questions about that? Okay, good. All right, I think that's about it. Lab 4, should say 4. And we're hung. Okay, awesome. Yeah, Lab 4 is posted, and it's due at the end of the semester, December 2nd, during the last lecture. Okay, so I can't give any extensions on that because the semester is going to end. Okay. No, there is. I think the last class is the 2nd. I don't think we have labs. I'll double check that. Okay. Okay, so I guess that's going to be hung. All right, so the TAs will give you further hints and insight into the Lab 4. I'll let them take care of that. Okay, so so as I mentioned, the Lab 4 is due on the 2nd. That gives you 3 lab sessions to work on it. And that doesn't include the labs that are going to be canceled because of Thanksgiving. So you have three lab sessions to work on that. I think, depending on, assuming you're done with lab 3 and you're fairly comfortable with it, I think that's a pretty decent amount of time, because you don't have to write a lot of new RISC-V code, and the changes you have to make to the lab 3 CPU are fairly minimal. The main challenge here is the stalls and testing and figuring out how you know if it's working when you got stalls in there, because and I gave you a test program in this fetch sequence. But remember, when you test branches and jumps, you're looking at the fetch sequence when you test it. So in the last lab, you probably were looking at the contents of the register file, right, to make sure that things were working. Whereas now, because it was arithmetic, right, it was all number crunching. Whereas in this lab, it's branches and jumps, so you're looking at the sequence of instructions that are fetched. So you're looking, the program counter is what's going to tell you whether it's working, that and the stall signal, right? So those are the two things you're going to base your functionality on. Okay. All right, so now we've reached the point in the class where I have finished all of the material that I needed to cover for you guys to design a CPU from scratch. So we can finally get into some more conceptual stuff. I've gotten all the practical stuff out of the way. So we have 4 more lectures where I'm going to devote to 4 different topics that don't relate to what you're doing in the lab. At least not directly. They're all concepts, stuff that that are important topics, but are not. It is not designed to help you get through the lab stuff. Okay, so the first topic is sequential logic. We've talked a lot about that already, but I'm going to give you more formal treatment on that, and then timing analysis, digital building blocks, and then CMOS logic design, and a final exam review. The final exam will be December 5th to the 9th, that week. You can take it any time during the week like you did the midterm. Yes?
On the syllabus, it says that the 14th was no lecture.
Yeah, so that's actually been changed. Normally I go to the supercomputing conference, but this year I decided the airfare is outrageously expensive, so I decided not to go. And I've got some colleagues that are able to do the stuff that I was supposed to do there in terms of running the meeting. So we're going to get an extra lecture as compared to last year. Okay, so sequential logic is logic whose output depends on input and some kind of memory, some historical inputs. But that's a very broad term. In this class, when we talk about sequential logic, we're usually talking about synchronous sequential logic, which is a little bit more specific, where it's synchronous logic with a clock. Not all synchronous logic has to have a clock. Okay? There's also asynchronous sequential logic, which is a topic that I learned when I was in undergraduate school, but it's really fallen. It's basically sequential logic without a clock, which you can do. Basically, you base it on changes to the input. The problem is it's very hard to design a stable asynchronous sequential logic circuit. And there was a lot of work done on that in decades past, because it would allow you to eliminate the clock and you save, it would be much more power efficient. But these days, I don't think anyone's doing asynchronous sequential logic anymore. It's all clock based. So as I mentioned before, there's 2 ways that I know of to do memory in Verilog. Maybe there's more. These are the only 2 I know of. If you write an always statement where you have an input that's not in the sensitivity list. So in the first example, always at positive clock, A gets B. B's an input, not in the sensitivity list. So the compiler says, well, that's got to be memory. The other way to do it is if you have an always statement and you don't assign all the possible outputs along all the control paths. So in this case, I say always at star, if A equals 1, then B gets C. Otherwise, well, what happens if A is not 1? Well, then memory, right? The problem is that the top one is the one you're supposed to use. The bottom one is called a latch, and you should avoid latches when you can. So a latch is basically, for example, if we take that always at star, if clock equals 1, Q gets D. So this is a different line of code than I had on the previous slide. This just says, this has a clock in it, and it says that if the clock is, it's basically equivalent to this code I showed, except now I call something clock instead of A. I think I called it, yeah, it's the same thing as this, except instead of A, I just called it clock. But there's nothing magical about that word. I just called it clock, right? So it's that, except I changed it slightly. So I say if clock equals 1, Q gets D. And in the bottom one, I say always at pause edge clock, if clock equals 1, then Q gets D. So what's the difference? The difference is that in the latch case, the output of the latch will be frozen unless the clock is asserted, in which case D gets passed directly through to Q immediately, well, after some propagation latency, right? So you see that, so clock, you could think of this as the door. You put the clock up and it opens the door. Then you change D and Q gets updated, right? But as soon as clock goes down, you close the door. And so when the clock is low, changes in D will not be reflected on Q, although that doesn't actually happen here, right? It does happen here, though, or actually it happens over here. So clock goes up high again, D goes low, Q goes low. D goes high, Q goes high. But then when I drop clock, it closes the door, so this change in D is never reflected in Q, right? So that's a latch. It's a level-sensitive memory where whenever the clock is high, it just acts like an open door that passes data through. When it's low, it closes the door, right? And it freezes whatever was in that memory element. In this case, Q. Q is what's in the memory element. It gets kind of frozen in there, right? On the other hand, a flip-flop or edge sensitive is going to respond to the rising clock edge in this case, because I use pause edge clock. So when I get a rising edge, it's going to take a snapshot of D, and then you'll see that reflected in Q. So Q will only change on the rising edge of clock. So there's 3 rising edges here, right? There's one here, and one here. So I've got 3 rising edges. So there's only 3 opportunities in this design here or in this timing diagram for Q to change. And of those, it only changes during 2 of them. So snapshot here, D is 0, Q goes to 0. Snapshot here, Q is 1, D is 1, Q goes to 1. And then I have a snapshot over here, which doesn't produce any change in Q because it was already 1, right? So I sampled 1, right? Does that make sense? So it's basically the rising edge of the clock takes a snapshot of D and moves it into Q. Now you might say, well, okay, well, hold on. What's the difference? Well, the difference is with a latch, you could hold the clock high for a long time. Whereas with an edge sensitive, it's like an instantaneous thing. How long does it take for the clock to go from 0 to 1 or 1 to 0? It's like really fast, right? Yes, it's fast. That's the point. But it's not perfect. You still have to keep the input stable for longer than just the rising edge or the falling edge of the clock. And I'll talk about that in the next lecture when I cover timing analysis. But in this case, you can kind of think of it like as, when the clock changes, when it goes high, when it has a rising edge, it's like an instant, very quick snapshot. Okay, so we talked already about how to design D flip-flops in Verilog. You can use always at pause edge clock or always FF at pause edge clock. And then we talked about enabled flip-flops. Some of you I noticed that there were some groups that were a little confused by this, I noticed, because this is what you used for the GPIO out, right? The GPIO out in Lab 3 was an enabled flip-flop. So the idea there was that you had to capture the input on the rising edge of the clock, but only during the one rising edge of the clock when you were executing the CSRW instruction, because otherwise you wouldn't be holding it long enough to see it on the display, right? It would change too fast to see it on the FPGA board, hex displays, right? So that's what this is all about. It's just basically adding an enable, and then there's a reset. Reset is what we do for the program counter. You reset it to 0 on a reset input. you guys actually were asking about, like, if I hit the reset, does the hex displays go to 0? And they would if you add a reset to the GPIO out register. But that wasn't, I didn't show that in the slides, I didn't mention it, so I assume most of you guys didn't do that. So when you hit the reset button on the FPGA board, you might have noticed that the hex displays just, yeah, they don't change, yeah, they freeze. Because if you hold in the reset and then flip the switches, they're not going to change, right? Because it's going to hold the program counter to 0, so the program won't convert the decimal, or the binary to decimal. But at the same time, it's not going to reset. The reset button alone doesn't reset the hex display. But you could have easily added that by just putting, if reset, a GPI out equals 0, right? Which we did for the program counter. And the instruction EX, too. Okay, so where am I going? Okay, so, this is I'm actually going to skip that. Okay, so you might wonder then, like, sequential logic, like what okay, aside, so far we've used it for what? Pipeline registers, counter, program counter is a counter, ticks up once a cycle. GPIO, what else? What else do we use sequential logic for? Well, the other big usage is for finite state machines. And a finite state machine is it's a circuit that is a way to add sequential behavior to a logic circuit. So I've harped on this idea that system Verilog is concurrent. It has concurrent semantics. Everything happens at once. But what happens if you want to design a circuit that behaves under certain, responds to certain patterns of inputs? Right? Now you might say, well, wait a minute, the CPU already does that. I mean, that's what the CPU does, right? You give it a pattern of instructions and it does different things. Yeah, but what if you were designing a finite state machine is when you have a dedicated hardware circuit that's designed to recognize patterns, not necessarily one that's built on top of a software hardware type system like we do. It's a simpler thing, right, than a CPU. So the example that the book gives for this, I don't know if this is the best example because it's a little naive, but they come up with this traffic light controller for an intersection. And the idea is that you've got two outputs here. So every FSM is going to have a set of outputs. In this case, we have a light signal that we want to have on an intersection. So one of the lights is on the A street, which they call Academic Boulevard, and the other light is on the B street crossing it, which is Bravado Boulevard, whatever they call it, right? So there's two lights, and those are 2-bit signals each because you want to be able to put a red light, green light, or yellow light. Okay, and then there's 2 inputs that indicate whether there's traffic on either one of those streets. So there's like a traffic sensor on each of those streets. So I know if there's traffic, that's my input, and then I can set the lights, the traffic lights is the output. And then of course there's got to be a clock and a reset. So a finite state machine has inputs and outputs, and then clock and reset. And the outputs are, responding to patterns on the inputs, right? Time series patterns. So that's what looks like in a cartoon form. So yeah, Academic Avenue, Bravado Boulevard, and then TA and TB are the lights on each street. And so in order to build a finite state machine, you have to think of what states the system could be in. And then you're storing the current state value in a memory, in a flip-flops, right, in registers. So the idea is that we end up with 4 states here that the system could be in, where you can have a green light on one street and a red light on the other street, or vice versa, right? Or you can have a red light on one street and a yellow light on the other, right? Or vice versa. So there's 4 different combinations. You don't have one obviously for both green, right? Okay, so in addition to having these states, you need to give them names. Now in this case, they gave them totally nonsensical names. S0, S1, S2, S3. I would have called it like go academic, go bravado, prepare to stop academic, prepare to stop bravado, something more meaningful, I don't know, right? But they gave them these four names, that's fine, S0 through S3. And then each state has a corresponding output state. So S0 is when green academic and red bravado, S1 is yellow academic, red bravado, S2 is red academic, green bravado, right? S3 is red academic, yellow bravado, right? So those are the so I have outputs associated with each state. You can also have outputs associated with the transitions. That's called a Mealy machine, but we won't cover that. I don't want to get too deep into this. The Moore style machine, which is what this is the simpler approach where all of the outputs are only a function of the current state, which means that the outputs are synchronous, right? The outputs can only change when the state changes, and the state can only change whenever there's a clock edge. So everything is synchronous, which means that like the inputs, the traffic sensors could be changing. They can have dynamics that are faster than the clock, right? In other words, the input traffic sensors might be changing multiple times between clock edges, but that's fine. It's not going to notice that. It's only going to look at what those inputs are on the clock edge, right? Which means that the outputs are synchronous, right? Okay, I'm only going to have fixed sample points. Each clock cycle is going to be one sample where I'm going to look at the inputs and decide what to do, right? And the system can only be in one state at a time, because this is a deterministic state machine. If you take a theory of computation course, you might learn about non-deterministic state machines where you can be in more than one state at a time. But this is these are deterministics. You're only one state. You can only be in one state each cycle. Okay, I can't simultaneously be in S0 and S2. Okay, so the transitions then are set up to tell you what the rules are in terms of going between to changing states, right? So if I'm in S2 here, I will stay in S2 as long as I've got traffic on Bravado, because I'm going to give Bravado a green light, and as long as there's cars utilizing that road, I'm just going to stay in that state. Once the traffic lets up on Bravado and the traffic sensor goes to 0, then I'll use that as an opportunity to change the light configuration. But I first must pass through this intermediate state where I have a yellow light on Bravado, right? And now you'll notice that this transition here doesn't have any input associated because it's unconditional, right? So that means that the yellow light on Bravado will be yellow for one clock cycle. Now the assumption here is the clock is very slow. Like it's like, you got to think of this as like a 10-second clock period, right? So you would be in this state for 10 seconds. So once you switch to S3, you'd only be in there for one clock period, and then you go to S0 where the lights would switch, and then I would stay there as long as I have traffic on academic. So there's a loop back transition. As long as I have traffic on academic, I'm going to stay in that cycle. The first clock cycle that I see no traffic on academic, then I will go to this intermediate state where I'll yellow light academic and then red light it in the next cycle. Does that make sense? So it's really simple. You might say, wait a second, as long as there's traffic on one street that's green light, then they'll never change. The lights will never, you'll starve the other street as long as there's a continuous flow of traffic. Yeah, that's right. In this design, that's true, because there's no like timeout period where you force the transition even with traffic flowing, right? So this is a really simple design. But you could add things here that would add a watchdog timer, right? That would say, oh, there's been, I've been in the green light on Bravado for, 2 minutes. It's time to switch, even though I still have traffic on Bravado, right? So that's the idea there. Okay, so you can build in a finite state machine. You could build a state transition table, which is just a truth table that you guys are used to from 211. The idea is that you have a column for your current state, and then you have columns for your inputs. And then your output is the next state. So what that means is that each one of these transitions is built by this table where the table itself is built as a combinational logic circuit that tells you what next state to go to, but that doesn't do anything until the next clock. Then you'll make the current state what this guy is telling you the next state should be. Does that make sense? So it's basically just every one of the arrows in that diagram would have a row in this table that would say, if you're in state S3, then I don't care what the traffic sensors is because I'm going to go to S0. That's my yellow light state. But if I'm in S0, which is my green light on Academic Street state, then I don't care what the traffic is on Bravado because they have a red light anyway. But as long as if the traffic is 0 on Academic, then I'm going to go to S1, right? But as long as I have traffic on Academic, I'm going to stay in S0. So let's fill that column in. There we go. Yeah, so if I'm on S0, which is green light Academic, I'm going to stay in S0 as long as I have traffic on Academic. If I don't have traffic on Academic, I'm going to go to S1, which is my yellow light on Academic, right? So you can build a diagram like that, and then I mentioned that so the other problem here is that we have names for these states, right? We have to also assign them codes, binary codes. So I'm going to do that here. So each one of these, there's 4 states, so I'll assign a 2-bit code for each state. And then you can replace the names in the truth table with codes. So now it's all in binary, right? So now it looks like a real truth table. And then I can just convert this into Boolean logic using the methods that you guys learned in 211. Right, so in this case, the next S1, so notice this is S1, I'm splitting both bits of the state out and separately because you can only calculate 1 bit at a time. So S1 prime, the next S1 bit, is just going to be the current S1 XOR the current S0, right? And then the next S0, and again, the S0 and S1 are just based on this encoding, right? The leftmost and the right left bit and the right bit of the state encoding. S0 is just going to be, this sum of products to calculate the next value of S0. Again, this is just stuff that you guys hopefully remember from 211 Boolean logic stuff. Okay, and then for the output, we have to assign codes for these colors for the lights too. So we'll say green light is 0, 0, yellow light is 0, 1, and red light is 1, 0. And so we can build a table that just maps the current state directly to the outputs. In this case, there's 4 total bits of output because there's 2 traffic lights and each traffic signal color is 2 bits, right? So you can build another truth table that just does that, and you've got, this is called the output logic. So we have the next state logic, which is concerned with the transitions between states, and we have the output logic, which is concerned with translating each state into its corresponding outputs. Make sense? So they're just 2 pieces of combinational logic. Right? You might be thinking, wait, that's a lot of combinational logic for a sequential lecture. Yeah, so the reason, the way this works is that, let's skip ahead a little bit here. So the way this works is that you're going to split your code into 3 pieces. So in System Verilog, you can start out by defining a custom data type for the states. And you could have also done this for the light colors too, but I didn't do that for some reason. So I have the state, so it says type def enum logic 1 down to 0 because I have to tell it I want to allocate 2 bits for the state. And then I can say S0, S1, S2, S3 state type. Now, by the way, I never can remember that syntax. I always have to look this up, right? But you guys should be familiar with enumerated types from Java and C and C++. It's a fairly typical. The idea is that you just give them symbolic names that represent numerical values, right? Now, in this case, we're telling the compiler that the enumerated type is 2 bits, but we don't tell it what 2-bit values to assign to each one of those. The compiler does that for you, right? So I'm just going to have a type called state type, and then I'm going to declare current state and next type to be that state type, right? Now again, I could have done the same thing for the light color. And by the way, you guys could also do this for instructions in your CPU, by the way, too. I think some of you, I suggested to do this, but in your control unit, you can have an instruction signal that's an enumerated type that will put the actual instruction in your waveform so you can tell what instruction your CPU is executing, like the mnemonic. So that's just different ways you can use these enumerated types. Okay, but it turns out that to build this finite state machine, the only actual sequential logic you have to put in is one thing here that is a clocked process that says, if you reset, go to the reset state, which is S0. They used to call that the sanity state. It's like a known initial state that when you hit the button, it goes into, right? Because when you start up a system, generally it's going to come up in a random state. Although on an FPGA, it doesn't, because you configure an FPGA and it rewrites everything on the chip to 0. But in an ASIC, an actual, like a normal chip that's not an FPGA, you'd bring it up into a random state. So the reset will reset it, but then aside from that, you just take whatever is the next state and you just make it the current state. So that'll take care of that'll synchronize everything and control the transitions. And then you can build the next state logic as a separate always block, but it's an always combinational, and it just sets the next state as a function of the inputs. Does that make sense? So this is just making that truth table that I showed. Now notice that I have a default though. At the first line of code it says next state equals current state. That means that if I don't match anything in that if statement, just assume you're going to hold in the same state. Right? So I'm just going to assume that there's an implicit, according to this code, I'm going to put an implicit loop back on every state that says, if none of the outgoing transitions match, just stay in the same state. Otherwise, if something matches in this if statement, like for example, if my current state is S0, S1, then I'm going to say the next state is S2 without even checking inputs, because that's one of those yellow light states that I just pass through. But on the other hand, if my current state is S2 and traffic on Bravado is 0, then I'm going to go to state S3 and I'm going to yellow light Bravado because I got no traffic left. Now notice I don't mention TA, traffic on academic, because it's a don't care, so it's just not referenced in that if statement. Okay, and then you have the output logic, which is another always statement that once again I'll set defaults for light A, light B, and then I will set my lights based on what current state I'm in. I could have used a case statement here, but I just used an if then else. Right? And actually, I think I know why I didn't use an enumerated type for the light colors, because if you use an enumerated type, the compiler decides what the encodings are. Although there's probably a way you can lock those down, like you can in C, right? But I didn't. I just put the binary values in here, right, just to be safe, because the traffic lights have, like wherever I bought the traffic lights, they're the ones that are going to tell me what codes I have to use to change it to a certain color, right? So I wanted to make sure my controller used the right codes. Yes?
So what would you do? You just make LA and LB 2-bit logic types?
Yeah, I think what you can do, if it's anything, I've never done this in Verilog actually, or at least I don't remember. But if it's anything like C and C++, you can just set the values in the enumerated. Yeah, you can probably just say up here, you could probably just say S0 equals 2 apostrophe B 0 0. I think. I've never done it, but it's possible. In which case you get the enumerated types and you get to assign them. You get to assign their values. But I'm just guessing. It's not a big deal. It's just a coding convenience anyway. Okay, so so the other thing I show in here, and I kind of breeze past this, but I'm also showing the Boolean logic version of this as well. So I took this code and I synthesized it myself manually into Boolean logic, and I put that in there, right? This is what you normally would do in like a 211 class. You would implement this in Boolean logic. In this class, it's not really that important because the compiler, the tools do that, right? You don't have to worry about that. You just write the code, and it'll generate the gates however the compiler does it. Okay, so then here's a timing diagram that shows an example of the operation. So over here we've got the next state and the current state. So the current state is 0, where I've got green on academic, red on bravado, and then I switched to the yellow light on academic here. Why? Well, that was because traffic on academic went low here. Right? Now you might say, wait a second, why does it take so long from the time the traffic A went down to the time I actually go to the yellow light state? Well, that's because that went down just after the clock edge. I just missed it. It just barely, you see that rising edge comes a little bit before that. So because that happened, I ended up having to basically wait another whole cycle. Because this guy is obviously those traffic sensors are asynchronous to the clock. And it just so happened to come right after the edge. So I had to pay a little extra time to wait for that. And then you'll notice that S1 is the yellow light and S3 is the yellow light, and those guys are only in there for one cycle because they have unconditional transitions out. They're only meant as show the yellow light for one cycle, right? Okay. Okay, I don't know if I want to go through this or not. This is an example I had on an exam a few years ago for an elevator controller. It was kind of the same idea. The problem is that if you were actually designing a traffic light controller or an elevator controller, you wouldn't do it with a finite state machine because you would do it with a microcontroller. You'd get an off-the-shelf microcontroller like the RISC-V CPU, and you'd write software for it. Trying to design a complex system with a finite state machine isn't practical, right? It's just not. That's what you use software for. Now you might say, okay, well then when would anyone use a finite state machine then? What's the point? Is that like an obsolete concept? No, it's not. They're used a lot. But they're not used for applications. They're used for circuits inside of a chip. So they're used often for bus controllers, for instance. So here's an example of one of those that's totally current. So there's this bus protocol called AXI, which stands for Advanced Extensible Interface, and it's what every one of you got in your pockets right now, because AXI is the interconnect, the network on chip protocol that's used in all ARM-based devices, which is what is in every cell phone in the world. ARM processor with the ARM system on chip architecture. And that uses AXI. AXI is also used on FPGAs. So the FPGAs that we use in this class, when you reuse those, when you take 317 and 313, you'll be using AXI on those. We don't have it on now because you guys didn't put it in your design, but when you use the system builder tools for Quartus, it'll put these AXI connections on there. Okay, so how does it work? Okay, AXI is a master-slave interface, which means that basically you classify everything on all the devices that are on the bus that can communicate on the bus have to be either a master or a slave, meaning that the masters can initiate transactions and the slaves can only respond to them, right? And that's how most buses work that way. But AXI is by far the most common, right? So now you can have devices, by the way, that have slave ports and master ports. That's allowable. You can do that, right? In fact, some devices do that. Like DMA controllers, for instance, will have both. They'll have a mixture. It just depends on what the device has to do, right? So you might say, okay, well that's fine. What is it? Just like SPI, I squared C, pretty simple. You just say, I want to access the bus, and then you arbitrate, and then you put stuff on the bus. No, it's way more complicated than that. In fact, there's like hundreds of signals in an AXI channel, in an AXI connection. Why is that? It's because the bus is comprised of 5 separate channels. So every connection on an AXI bus actually has 5 separate sub-channels inside. Right? So there's one for read address channel, write address channel, read data channel, write data channel, and response channel. Now, the reason for that, you might be, well, why all the complexity? The reason they do it that way is because they want you to be able to overlap transactions. They don't want to say, I need to read something, and while I'm reading it, everything stops, right? They want to be able to issue requests to read and requests to write, but have, like, be able, while the latency of those requests is in progress, they want to be able to do other things on the bus, right? So they've separated it out where each of these things are arbitrated separately, right? So in other words, if I want to do a read, I can request a read, but the way I do it is I request it on the read address channel, right? And then whoever the slave is on the other side of that channel will say it'll get to do it at once, right? And consider that request. And then whenever it's ready, it can process the response to that read on the read data channel, right? Likewise, if I want to write, I put a request out on the write address channel, and then I use the write data channel to actually perform the write. Now keep in mind that each one of these channels, except for the response channel, is potentially pretty big in terms of number of bits. Usually the address channels are at least 32 bits just for the address itself, not counting the control signals that do the handshaking. And the data channel is at least 32 bits, although modern devices like your phones are going to have a 512-bit to 1024-bit data width, because they do that to get to move a lot to improve throughput, right? They're parallel channels, right? Okay, so where am I going with this? Well, it turns out that in order to talk on an AXI channel, on an AXI bus, you have to go through a bus protocol, right? You have to do a handshake, and the handshake has to happen on each of these channels separately. So how do you handle that? Well, the handshake is a sequence, right? You say, I want to do it. The other side says, okay, you can do it. You say, I'm doing it. Then the other side says, I acknowledge you did that, right? There's a back and forth conversation that happens. And so each stage of that conversation has to go through steps, a sequence. And there's a state associated with all of the partially completed forms of that handshake process, right? So when I say, I want to talk to you, I want to send you an address. Okay, wait, I'm doing something. Okay, you can tell me, what do you want? What's the address? Okay, I'll take the address, I'll think about it, and send you a response when I'm ready. Meanwhile, it'll synchronize, send the response back. So there's all this kind of communication that happens. So this is the timing diagram that shows how a write happens. This isn't a read. Reads are a little bit more complex, but this is a write transaction. Now keep in mind, by the way, too, that the AXI bus, like most of bus protocols, are based on read and write operations, load and store, also known as programmed I/O, where the master says, I want to read or write with a specific address. That address is addressing a target on the bus, some peripheral, right? And then it'll write data that it wants to convey to the peripheral, or it'll read something back from the peripheral that allow the peripheral to send data back to the master, right? But it's all initiated by the master, right? Does that make sense? Now, by the way, some of these protocols, they're getting rid of the master-slave terminology. Sometimes they refer to it as like controller and subordinate, or controller and endpoint. It's a little, but the problem with that is that it makes it a little bit more confusing in my view. But the master-slave terminology is a little out of date, but there's no mistaking, what that means, obviously. But that was the historical terminology that they used. Let's see. So what is the sequence here? If I want to write to an endpoint on the bus, I need to follow at least 7 steps. I need to drive the AW address when I say drive, I mean put an address. What address do you want to write? What's the address that you're writing to? And I need to assert AW valid. So here we go. There's the address, and there's valid, right? Now, this is a handshake, so the idea is that what I'm expecting to happen in the next step is the slave is going to assert ready. That's my response. That means I know you're trying to access me, I'm ready, right? But you don't know how long that's going to take. You could be waiting for hundreds of cycles, right? So this is the part where you have to go into a state where you've requested access, but it hasn't been granted yet. That's a state, right? So in this case, it comes back right away. Like one cycle later, boom, it's quick, right? So I request it valid, and I get the ready back, right? Then after that, I'm like, okay, I told him I'm writing. Why? How's it know you're writing? Because I use the write address, bus, channel. Because I use the write address channel, it knows I'm writing. And I gave him the address, and he accepted it. He said he's ready. I'm done, right? My work is done here for now, okay? But then the next step is I have to actually give him the data I want to write. But that happens separately, and I can wait to do that, although typically doesn't happen. The next step is I need to go to the write channel, the data write channel, and I need to assert ready and wait for him to give me a valid, right? When that happens, then I can put my data out that I want to write, and there's this additional signal called W last. It's used for bursts. Sometimes I might want to write a sequence starting from that address. This might be the base address. I might want to send 5 words. But in this case, assuming I'm just doing a one-word transaction, I will assert last on my first data beat, my first data word, right? And then AXI has this feature that has this acknowledgement channel called the B response channel. Because otherwise, you don't really, like the problem with writes you don't really know if it worked. Like you say, I want to write. How do you know your write just didn't go into a black hole, right? You need to have some acknowledgement. So there's this acknowledgement channel, and for that, in order to get my acknowledgement, I have to assert be ready, and then I have to wait for the slave to assert be valid, and he'll send me an acknowledgement code in B response, which will tell me, it'll give me an update. Like, did it work? It worked? Oh, there was an error? Oh, I shouldn't have wrote to you. I wrote to the wrong address. You get a feedback from that, right? Make sense? Now this is real. This is, like I said, this is what everyone's using right now on ARM-based systems. So how would I design an interface? Like, for example, if I wanted to allow your CPU, the CPU design in this class, if you make it AXI compliant, then you could take your CPU and drop it into anyone's cell phone, and it will be a master in there. It will be able to do transactions in any, because this is a standard protocol, right? As long as your CPU has the ability to speak AXI, then it will be able to talk to an Apple A15 processor, right, in an iPad, right? It'll be able to talk to stuff on there, right? So how would you design that? How would you do that? How would you create a dialect? How would you give your CPU the ability to speak AXI? Well, generally the way you do it is you create an interface. So you would present your CPU with a simple interface, like, for example, on the left side of this design, I can create a module that will say, write address, write data, and write enable, right? That looks familiar, right? That looks like your register file, right? So you can give it an address and a data and a write enable and to tell it to write. And then this guy has to have a feedback called busy that says, okay, I'm working on it. Don't just give me one, I can only do one of these at a time. Actually, that's a limitation of this design. You could design something that would process multiple outstanding requests, but this one's simple. So there's a busy that says, don't bother me, I'm working. And then there's an error feedback that'll say error. And usually in an ARM processor, like the one in your phone, if you get an error from an AXI, that usually, that's caught by Linux. Linux will handle that as an exception, usually crashes. That usually means seg fault if that happens. If you have an operating system. If you're running bare metal code, then you're in trouble because you would have to manually check for error conditions like that, or put a handler in there for that. Okay, so that's the processor side. That's your CPU has a simplified interface. Just I want to write to this address. Tell me when you're done. On the other side, these are all the signals I need to talk to AXI. And these are just the ones I mentioned. Some are inputs, some are outputs, but this is what you plug into this will become your master interface, your AXI master port that you can then plug into an AXI interconnect, which then gives you basically network access to the chip on your phone, right? Okay, so you would have to design a finite state machine for this, which I did. And keep in mind that this is just for writes. This doesn't handle reads, it doesn't do bursts, it doesn't implement all the features of AXI. But if you're just concerned about doing writes, this is I think as simple as you can get. So I have an idle state there where it's just idle. I'm not talking on the bus. That state is, you leave that state whenever you get a write enable signal from the CPU. Okay, so your input, I put the inputs here in red. So the input conditions on these transitions are marked in red, and the black are the outputs associated with each state. Now you might say, wait a minute, why didn't you put the outputs inside the state? I don't think I can make it fit, so I just put the outputs next to the state. Okay. Also, I gave the states reasonable names this time, not like the book did with S0, S1. So I have idle. I have a state called request to send address. So in that state, I'm going to set busy to 1. So I'm going to tell the CPU on this side, you hold off, I'm working on this. And I'm going to set AW valid to 1, which is the first step to initiate. So I go to the address write bus, I say set that to 1, and I wait for AW ready to be 1 coming back. That's my arbitration. This is the handshake. I want to write, okay, you're clear to write. At which point I take the address valid, put that high, and address write address to be write address, which is, so this is basically a mux where I take whatever the CPU gives me as the write address and I pass it out to the bus. Before that, I was just putting zeros, although you could put X's or Z's. But I'm just assuming that when I'm not actually, like in the timing diagram here, I'm assuming that whenever I'm not doing something like this red, I'm just assuming that's 0. I may not need to do that, because that red's usually a don't care, but I'm just going to assign all that red stuff 0. And the way you do that is you set, I have a default AW address is 0. If I don't specify it as an output, it's 0. Well, I do specify it here, that's when I put the address out, okay? Then, just like the traffic light controller, when I'm in a yellow light, I transition, I'm only in there for 1 cycle. So I unconditionally go to the next stage, right? You might say, well, why? Because the protocol says that you may have to wait a while to get this ready, but once you get the ready, it's exactly 1 cycle, right? At least 1 cycle per address. I might want to, maybe I can give it another address, but if I'm only doing 1 word transaction, I got to bail after 1 cycle of sending that address. So basically, this cycle here is going to be the cycle where I'm in that state called send address, right? Then I unconditionally leave that and I go to wait for ready, at which point I just wait for W ready to be 1, right? And I think I forgot to put, hold on. I think you're supposed to have, never mind. Yeah, I think W valid should be high in that state too. I think that the W valid should be high. Yeah, because I don't think ready will go high unless W valid is high. But anyway, you set that to high there, and then you come in to send data. You're there for 1 state. So this is I'm waiting for it to be ready. This is an unconditional transition out because I only give it the data in 1 cycle, and then I leave. And then I just basically repeat the handshake a 3rd time now for the response channel. So I set B valid, or I set B ready to 1. I wait for B valid. And then I get the response, which can either be an error signal, in which case I go to an error state and I get stuck there forever, because I assume the whole system is now crashed. Or I go back to idle, in which case the CPU will see the busy go low and it knows that the transaction is completed. Right, so so you can tie your CPU into this interface pretty easily, assuming you have you have to put load and store instructions in, but you could set it up where a load or a store from your CPU will go out to this guy, or you could even add a special instruction that does, AXI write, whatever you want to do. But you could use a CSSR instruction for that matter if you wanted to. But this would give you the ability to simplified interface on one side and then AXI compliant on the other side, right? Right, that's the idea. So how would you build this? Well, this is the whole code. I know it's a little small. I don't know how easy it is to read, but this is the module. I put all the inputs and outputs here for both sides of the connection. I have my enumerated states. I only need 3 bits for my state because I only have 8 states for this thing. I've got state and next state. There's my clocked process. That's my next state process, and that's my output process. It's pretty simple. I took some shortcuts here, though. Like, for example, with my output logic, I specified all my defaults here, and then I just had special, depending on what state I was in, they would have special signals associated with them, so I just set this with an if statement. Down here, my next state logic, I also just, I use the case statement here, and my default next state was the current state, right? So I always stay, by default I'll stay. Yeah, so that's basically it. These state machines are divided into clocked process, next state process, and output process. Only the clocked process is actually clocked. The other ones are combinational, just always, always comb. Okay, makes sense? So that is what you use a finite state machine for, not for an elevator controller or a traffic light controller, because again, those would be controlled by software. But stuff like this is very common whenever you have to you have to talk to a bus or some kind of handshaking protocol. Yes.
So I was just curious, if you go back to the waveform you were showing us, this one. So you said that you do the valid, right, and you wait for the ready. Mm-hmm. And then later, when you do the data part, you also do a similar thing where you do the ready and wait for the valid?
Yes, yeah, I might have.
Or is it?
Let's see, did I screw this up? So valid goes high, then ready. In this case, ready goes high, then valid. Yeah, so they're swap. This is what's confusing about AXI, right? The names are, I don't understand why they don't call them request and grant, right? It would make more sense. Instead of request and grant, they have ready and valid. So the order is, on the address channel, it's valid, then ready. Valid is request, ready is grant. On the data channel, ready is request, valid is grant. And on the B response channel, ready is request, valid is grant. So these are just single bit signals. And they go in opposite directions, obviously, but the naming is confusing. But the timing is really simple. You just assert the request and you wait for the grant to come back and then you move forward, right?
So could you then, is it possible to do the valid and the ready at the same time for say address and data? You were looking for
it actually possible. So there's 2 versions of the AXI protocol. There's full AXI and there's AXI Lite. With AXI Lite, that's how it works. The data and the address go out at the same time. But this is the full AXI. This is the real deal. The AXI Lite is used for simple peripherals that are not that they don't want to have to worry about long latencies for accessing them for whatever reason. So if you have something like a simple RAM or something, you might use AXI Lite. Whereas this is the full-blown AXI protocol here, and so you have to arbitrate. You have to perform these in sequence. You got to do the address channel, then the data channel, then the response channel, which means that it's slower, but it's more robust. And this also supports bursting too. So I can make one request on address, and then I can send 1,000 words on data, which is fast if I do that burst mode, right? Whereas AXI Lite, I don't know if it supports burst or not. I think AXI Lite's usually for single word transactions, whereas full AXI, you can do bursts. And there's also security features built into this too, and there's some other,
How did you support burst?
I didn't put in my code. I don't even have reads. My code doesn't even do reads, it just does writes. I don't even have the ability to read a word. So it's pretty simple. If I had more features, it would be too big to put on a slide.
Yeah.
But I just wanted to show you an example of the kind of stuff you normally would have to design an FSM for.
Cool. Really cool.
Okay, sounds good. Then in the next lecture, we'll talk about timing analysis. Oh, you've got a quiz too. Quiz 4 is online. So don't forget to take that. It's due in a week.